All right, so this video is going to go over pages 27 through 30. This is going to be a relatively quick lesson, okay, because we're just going to talk a little bit about instantaneous velocity. So instantaneous velocity means you got something like a non-uniform motion going on. So we have like speeding up, slowing down, so it's just not constant. So if I had a graph that looks like this, a curved line going up, okay, this is actually what speeding up looks like. You're covering more displacement per unit of time. Your slope gets steeper and steeper as you go up. So that would be speeding up in the positive direction. So it's still going in the positive or forward direction. Now, if you're trying to find velocity on a line that's always changing, you can't really find slope anymore. So if I wanted to find velocity at this point right here, what I would need to do is I would take a straight surface like a ruler, a notebook, anything like that. And basically what I would do is I would trace a tangent line that bumps up right next to that point. It doesn't go through the line, okay? So I shouldn't see any lines that are like going through it like this, okay? You just want something that's gonna bump up next to it, okay? So just something that briefly touches that point and just keeps on going. Now what you did is you created a straight line where you can find the slope of it, and that will tell you the velocity at that point. So what I would do is I would pick any 2 points on the line I just drew. Again, that's called a tangent line. And you would just plug those 2 points into slope formula, and that would tell you your velocity. So if you want to find the velocity at a specific time, you need to draw that tangent line, and then you need to find the slope of that tangent line. So the velocity of at a specific time equals the slope of a tangent line. Okay, so that's your key takeaway on instantaneous velocity. Is when we have a curved line, we're going to draw that tangent, plug it in for slope, and then we're good. Okay, so now if I have the next one, okay, so let's say I have a slope that looks like this. This would be an example of slowing down. Because if you look, your slope is getting flatter and flatter as you go on in time. Okay, so that means you're slowing down. Now you're still going in the positive direction. You're not turning around and going opposite direction. Okay, you're still going in the forward direction. You're just slowing down. So if I wanted to find the velocity, let's say like right here, what I would do is I would trace a tangent line that bumps up next to that point, kind of like this. And I would pick 2 points on that line and plug it into slope. Or if I wanted to find the velocity right here, I would just draw another tangent line that bumps up next to that. And then I would pick 2 points on that line. Okay, so the key thing there is you can't just have one tangent line fits all points on a changing velocity graph. Okay, so you're going to have a different tangent line for each moment in time because your velocity is constantly changing. Now, you can still find instantaneous velocity on a graph that looks like this, okay, but you don't need to draw a tangent line here, because if I want to know what is the velocity of this point right here, you can draw a tangent line if you want to, but it's just going to be the exact same thing as the line that's already there. Okay, so instantaneous velocity can still be found on a uniform velocity. It's just all you gotta do is pick 2 points on the line. You don't need to make anything more difficult than it is. Okay, so if we go on the next page, let's investigate what's happening here. So it's a little bit blurry. Okay, so what's going on in this D versus T graph? One, it is speeding up because we're covering more displacement in a shorter amount of time, and it's still going in the positive direction. Now on this one where down here it says refer to the graph shown below, I'm going to use the graph up here on top, okay, because there's a lot less going on and it's basically the same graph. Now the reason why we threw this average velocity one back in here is because I want to make sure you know the difference between instantaneous velocity and average velocity. Okay, so average velocity, what we're going to do is we're going to look for the velocity between 0 and 4 seconds. So I'm looking for the gap between here and here. Now, a tangent line wouldn't touch those 2 points. So you could draw a tangent line bumping up next to them, but that would find instantaneous velocity. If you want to find average velocity, you would connect the 2 points. Okay, so I have 0, 0, and then I have 4, 4. Okay, so average velocity, all you gotta do is just connect the 2 points, plug it into slope, and that's it. So I would see y2 minus y1, so 4 minus 0, over x2 minus x1, so 4 minus 0. That's going to give me 1 meters per second. Okay, so average velocity is when you can connect the 2 points. If I wanted to find instantaneous velocity at 4 seconds, I would have to draw a line that bumps up next to it. Like this, I would have to draw a tangent line and find the slope of that line. It wouldn't do me any good for what is the velocity at 1 second or 2 seconds. It would just tell me the velocity at that time only. Okay, so that is the difference between average and instantaneous. So if we go down here to this next one, okay, the lines could have been a little better. Okay, so I'm only going to do I'm going to do the 6 second one on here because 4 and 3 just kind of aren't that good, and you kind of get some problems on there. So I'm going to do is I'm going to pick 2 points. So this 6 seconds, that's the velocity we're looking for. Is I'm going to try to find, like, I'm going to show you this line that I'm looking at. I'm looking at this line right here. Okay, I'm going to try to find 2 clean points on this line. Now, you're not always going to find exactly whole numbers, okay, but you can get decimals, that's fine. But I'm going to look for things like 0.5, something that makes it easier on myself. So if I follow that line all the way down, I see that it ends right here. So I would choose that point. So that'd be an easy one. That's 3, 0. And then I would choose another point. I think I chose the one right here, where that would be 7, 11. So again, the longer the line you draw, the more choices you have of points to pick from. Okay, so I'm going to do my slope. Okay, so at 6 seconds, I'm going to do y2 minus y1, so 11 minus 0, over x2 minus x1, so 7 minus 3. Okay, that's going to give me 11 over 4. And that's going to give me 2.75 meters per second. Okay, so that's what I got. Now, when it comes to tangent lines and instantaneous velocity, there is room for error. Okay, so your line may look a little bit different than mine. Okay, that is okay as long as we're close. Okay, as long as you're kind of in the ballpark, that's what we're looking for. We're looking for, did you draw the tangent line correctly? Did you pick 2 points on the line? Did you plug it in slope formula correctly? If you're doing that, then you're okay. If you got something like 3.5 or like 2 and stuff, that's going to be fairly close enough to where that thing's just going to happen. Okay, so there is going to be some wiggle room there on instantaneous velocity because you're drawing your own line now. So that's just going to happen. So if we go to this next example right here, I want to find instantaneous velocity at 2 seconds. Okay, so at 2 seconds, what I'd do is I'd draw a little point right there, and I would draw a tangent line that bumps up next to that. Now, it's a little bit harder for me since I don't have a straight surface to trace a line with, but my line would look something like that. Now, the points that I got is my y2 was 15, my y1 was 0, okay, my x2 was 3.5, and my x1 was 1. Okay, so those are the 2 points I got. So if you got something different on yours, as long as you're kind of fairly close, what I'm looking for is, did you get something around 7 meters per second? Okay, so if you're somewhere along that and stuff, that's close enough. Okay, so on 3 seconds, I'm going to change the color up. So at 3 seconds, what I would do is I'd have my point right here, and I would draw a tangent line that bumps up next to that point and keeps going. It looks like that. And the points that I chose for that, my y2 was 40. Okay, my y1 was 0. Okay, my x2 was 6, and my x1 was 1.5. And I got about 8.89 meters per second. Now, as long as you're somewhat close, that's fine. But the main thing what I'm looking for is, on this graph, we know that we are speeding up as we are going up. So your velocity should be showing me that. So at 2 seconds, we had 7 meters per second. At 3 seconds, now I have 8.89. Okay, so you're showing me that it is speeding up. That's what we're looking for. Okay, and we'll do the 6 seconds, the 4 second one. So what I would do is I would figure out what is the velocity at that point. So I'd draw a tangent line that bumps up right there. Okay, and my point, so I'm not going to really worry about points at this point because you're kind of figuring out that. Okay, I got roughly around 13 meters per second. So as long as you're close, okay, as long as you're showing me that you're increasing your velocity, you're drawing your lines correctly, you're picking 2 points, and you're plugging in a slope, that's what we care about. And then next example, I'm not going to really worry about this one because this one has even more room for error. You'd actually have to connect these dots kind of like this. And then you would find the slope of those same points. It'd be the same thing. It's just a different one. And now there's more room for error because you actually have to draw in the line. Okay, so I'm not going to really worry about that one because it's just the same thing as the one we just did. So let's move on to the next page. That one, we're going to do a little bit of a review of your different types of velocities, and that will finish up this video. Okay, so constant uniform velocity, that means we're not changing. So the rate of change in an object's position is staying constant. So what that basically means is if you're covering, like, let's just say a displacement of 5 meters every second, if you're covering the same 5 meters every second, that would be constant velocity. Now, if you start bumping that up, where now you're covering 5 meters a second, then you're covering 6 meters per second, then 7 meters per second, that would be speeding up. Okay, so constant velocity is where you cover the same amount of displacement per unit of time. So a couple ways you could find that. One is if you're on a graph, you would just find slope. Okay, or the equation is V equals displacement over time, which is just your final position minus your initial position over your final time minus your initial time. Okay, which is basically slope. Okay, this would be your change in Y. This would be your change in X. Okay, so same thing. It just depends on if you're on a graph or a word problem. If you are on a graph, so a graph would look something like this. You're just looking for a straight diagonal line like that. Okay, and this is a position versus time graph. So that would be a constant velocity. And if you're looking for examples, you can go back to pages 20 through 21, and that's more examples there. Now, if we go to average velocity, okay, that is going to be the slope of a line that connects 2 points. Okay, so if you're looking at a graph, we'd find the 2 points that we're talking about, connect them with a line, and then find the slope of that line. Or we did some word problems where we actually had displacements and times, and we just added up the displacements over the total time. And we'll go over that equation here in just a second. On the equation, it would be slope. If you just connect the 2 points, find the slope of that line. That's how you do it on a graph. Versus an equation, remember we had V average equals total displacement over total time. So that's where you would add up all your displacements on top, add up all your times on bottom, and then take top divided by bottom. Now on a graph, what it would look like, so if I had a position versus time graph, and let's say my graph looked like this, where I have a constant velocity going in the positive direction, and then I stop for a little bit, and then I turn around for a constant velocity going back, and I end here. If I want to know the average velocity from where you started and where you ended, I would just connect these 2 points and find the slope of that line. And then if you want to look at more examples of that, 22 through 26. Okay, so pages 22 through 26. Then instantaneous velocity, the one we just covered. Okay, that is going to be the velocity at a given point. So I want to know what is the velocity at that exact point in time. And this is more likely going to happen on a problem or a graph where it's speeding up, slowing down, okay, and less likely on where you have constant velocity because it would just be a straight line anyway. So if you want to find, there really is no equation for that. What you would do is you would just find the slope of the tangent line that you drew. So that little line that you traced bumping up next to that curve, you just find the slope of that. So if I had a graph, so position versus time, and let's say I have an object slowing down in the positive direction, I want to know what is the velocity right here. Basically what I would do is I would draw a tangent line that bumps up next to it and find the slope of that line. And if you want to know what pages, well, we just kind of went over those, so pages 27 through 29. And that ends that video, so the next one is going to be the review.